Hey guys, welcome back to another video in the Digital Logic series. Today we're looking at a problem from the textbook about simplifying Boolean expressions and sketching gate diagrams. So in our last video, we looked at how to construct truth tables to verify logic, but writing the equation that passed the test bench is really only half the battle. So if you hand in a raw, unoptimized Boolean equation directly to either a manufacturing team or you drop it into an FPGA, you're wasting physical hardware space, you're burning unnecessary power, and then you're as well adding propagation delays. So every single logic gate your signal has to pass through takes a physical amount of time to change its output state. And if your circuit contains redundant states, your clock speed starts to drop. So that's why we use what's called Boolean algebra. It allows us to mathematically simplify equations down to their minimum state before the physical hardware part. So on screen, I've put up a cheat sheet of foundational Boolean theorems that you need to know. Don't waste time trying to sit down and force memorize this entire list right now, because as you start to practice and go through more and more problems step by step, patterns like the De Morgan's law, inverse law, absorption law, these will all become second nature to you and you'll start to spot them instantly. So today we're going to use these laws to go through 3 common exam style problems. We're going to simplify them first and then sketch the logic circuits with the minimum number of gates. So let's get right into it. The best way to start these type of problems is, in my opinion, by going for the low-hanging fruit first. So we notice that we're able to use the commutative law quite easily on the terms BC and BC naught. What we can do is factor out B, leaving C or C naught, and we know from one of the laws that C or C naught just becomes 1, so we can drop it out entirely. And then this will leave Y equals B or A naught, B naught, C naught. Then, once we see we have this, we're left with a single literal B added to a product term that actually contains its own complement, B naught. So this would be a classic setup for the elimination theorem, which is a variation of the distributive law. Because B is already adding a logical 1 to the circuit whenever it's true, having B naught in the neighboring term would be redundant. So the B naught term will drop out completely, leaving us with our final expression of Y equals B or A naught, C naught. And then from here, we'll sketch a simple circuit diagram. We know that the two terms here, two variables here, A naught and C naught, will be going through an AND gate. So we'll write them next to each other. Because the terms are have a not operator on them, we'll write the operators like so and then put them through an AND gate. And then the terms are going through an OR gate. So we'll connect B to the OR gate and then C naught and A naught. And then this will have our final output of Y. So your final answer will be this. When looking at this next expression, the lowest hanging fruit is that middle term wrapped in parentheses with the inversion caret next to it. Anytime you see an inversion encompassing an entire product or sum, your first instinct should be to apply De Morgan's theorem. And an easy way to remember what De Morgan's theorem is you flip the signs and the primes. So that means B will become B prime, and this is an AND operator separating B and C naught, so you'll flip that to an OR operator, and then C naught becomes C. So once you've applied De Morgan's theorem, this is what you get, and we can substitute it back into the main equation, which will give us Y equals A prime B C or B prime or C or B and C. Now, for our next step, we want to look at for a way to factor this down. Notice that the first term, the third term, and the fourth term all share a common literal C. So what we can do is we can pull that C out completely from those terms, and we can leave b prime by itself on the outside. So after simplifying, we can get y equals b prime or c a prime b or 1 or b. And if you look closely at what we have inside the parentheses, we have a prime and b or 1 or b. According to the null law on our cheat sheet, anytime you or any Boolean expression with a logical 1, the entire expression is equal to 1. So this whole thing will be set to 1, which will give us y equals b naught or c and 1. And from here we know c and 1 is just c. So then our final simplified equation will be y equals b naught or c. And to draw this simplified gate diagram, you'll do b and c for literals. B will be inverted, and then both will go through an OR gate, with the output being y. And this is your final answer for part B. Finally, let's move on to problem C. This problem looks very intimidating at first glance because of the nested parentheses and multiple inversion bars, but just like the previous problems, the best way to start is looking for the low-hanging fruit. If you notice this inversion bar and your first idea was De Morgan's law, that is a good idea, but before we do that, we're actually able to simplify within the parentheses, and it'll make it much easier in the end. So looking inside the parentheses, we have a or a prime and b or a prime and b prime. We notice that we have like terms with the a primes, so we can factor that out. This will give us a or a prime, b or b prime. And we know that this becomes 1, leaving behind a or a prime. And we also know that this simplifies to 1 as well. So then we'll get y equals 1 or a or b prime prime. The complement of 1 is 0, and adding 0 to an OR gate changes absolutely nothing. So what we can do is remove it entirely from the equation. This will then leave us as y equals a or b prime prime. Now here is where you can apply De Morgan's theorem. And remember, De Morgan's theorem, flip the signs and the primes. So a will become a prime, the or will become an and the b prime will become b. So this leaves our final simplified equation, y equals a prime and b. And to sketch the simplified gate diagram, we'll write our variables a and b. A will be inverted, and they will both pass through an AND gate with the output y. And this is your final answer. That's all for this video on simplifying expressions using Boolean algebra. Thanks for watching, and if you have any questions on these examples or suggestions for any problems you want to see in the future, just leave that down in the comments below. And make sure to check out any other videos on my channel if you need any additional help. See you in the next one.